Hello, cosmic explorers. Welcome to our latest journey where we uncover the mysteries of the universe. Today, we're delving deep into the phenomena of the terrifiant blinking stars, those intriguing celestial bodies that twinkle mysteriously in the night sky. Are you ready to travel through space and time to uncover their secrets? Let's launch into this cosmic adventure. Consider this: if the Big Bang sparked the creation of our universe, could it be that all life also burst into existence from a similar cataclysmic event? Our world operates under the influence of countless cycles. Everything concludes only to begin anew. Take the seasons, for example, which shed the ripe fruits from trees, laying down seeds that will sprout into new life, brimming with energy. And what if this cyclical nature extends to the birth of life across the universe? Imagine that the genesis of all existence might be linked to a grand cycle reaching its climax. Dear traveler, today we embark on a journey to explore the stars that have experienced dramatic and awe-inspiring transformations through violent explosions neutron stars. Thanks to cutting-edge research and the power of space telescopes, we're learning more about these celestial bodies. Although they've been extinguished for millions of years, they serve as vital witnesses to the cosmic history that shapes our universe. Embark on a journey into the cosmos as we delve into the enigmatic world of astrophysics, exploring rare celestial objects that hold the secrets of the universe. Are you ready to uncover the mysteries that set these unusual stars apart? But before we launch into the unknown, make sure to like this video and subscribe to our channel to stay updated on all our cosmic adventures. Thank you, and prepare for an extraordinary journey. Long before the discovery of the first neutron star, the concept had already been hypothesized in the early 1930s by Soviet physicist Lev Landau. This bold idea followed closely on the heels of another significant breakthrough in 1932, when British physicist James Chadwick discovered the neutron. But let's take a moment to understand the basics. What exactly is a neutron? A neutron is one of the three fundamental particles that compose an atom. Within the atom, a cloud of electrons orbits a nucleus, which itself is made up of protons and neutrons. Unlike other subatomic particles, the neutron does not carry any electric charge. Protons carry a positive electric charge, while neutrons, fascinatingly, are electrically neutral despite having a negative charge at their inner core and outer edge, separated by a positive charge. This nuanced structure of the neutron, discovered by physicist James Chadwick, not only reshaped our understanding of atomic physics, but also earned him the Nobel Prize in Physics in 1935. His discovery opened countless doors across various fields, including astrophysics. During this period of intense scientific innovation, physicist Lev Landau proposed a groundbreaking hypothesis: could stars be primarily composed of neutrons? This idea spurred further exploration by two more visionaries in the early 1930s. In 1934, Swiss astrophysicist Fritz Zwicky and German astronomer Walter Baade took the concept further. They considered the structure of atoms mostly empty space and postulated a revolutionary idea. What if atoms could be compressed to the extent that this space was completely eliminated? This would result in a state of matter of extraordinary density. These thinkers were on the cusp of proposing what we now understand as neutron stars, celestial bodies whose unimaginable density and peculiar properties challenge our grasp of the physical universe. Imagine a hypermassive star at the twilight of its existence, having depleted all its nuclear fuel. Such a star, in the final throes of its life, might undergo a spectacular transformation due to a supernova triggered by its own gravitational collapse. In this cataclysmic event, the outer gaseous layers of the star are violently expelled into the cosmos, leaving behind what resembles the bare core of the star. This newly exposed core, extraordinarily compact and dense, would primarily consist of neutrons. Thus was born the concept of the neutron star, a celestial object so dense that a mass comparable to our sun could be squeezed into a sphere with a radius of merely 10 kilometers. However, it wasn't until decades later that the study of these intriguing stellar remnants truly began to accelerate. For a star to follow this evolutionary path and become a neutron star, it must possess specific characteristics. Not all dying stars undergo this transformation. The most massive stars end their lives as stellar black holes, while the more common, less massive stars become white dwarfs. This discovery not only expands our understanding of the cosmos, but also challenges our perceptions of the physical limits of matter and the ultimate fate of stars. For a star to transform into a neutron star, it must start with a mass between 6 and 30 times that of our Sun. These stars, often termed as ordinary stars, lead fascinating lives that culminate in extraordinary endings. Yet before the true nature of a neutron star was unveiled, we relied on pivotal discoveries that pushed the boundaries of our understanding. It was not until 1967 that we got our first glimpse of what a neutron star might look like, thanks to a groundbreaking discovery by a PhD student whose work was controversially credited to her professor, Anthony Hewish, at Cambridge University. They detected PSRB 1919+21, an exceptionally unusual neutron star. Despite their commonality, neutron stars were beyond our observational capabilities due to their incredibly modest size, until this point. However, PSRB 1919+21 wasn't just any neutron star. It spun rapidly, generating a strong magnetic field, and functioned like a cosmic lighthouse, beaming radio waves at regular intervals. This pulsar, located in the northern constellation of Vulpecula, was the first of its kind to be detected and extensively studied. In 1968, another milestone was achieved with the identification of a second pulsar in the heart of the Crab Nebula. This pulsar was none other than the afterglow of the supernova SN 1054, which has been observed since the year 1054, offering scientists a rare and extended glimpse into the life cycle of stars. The mysterious link between pulsars and neutron stars was firmly established through the historical observations of supernova SN 1054, documented extensively by Chinese and Arab astronomers. This connection demonstrated conclusively that neutron stars are the remnants of supernova explosions. The investigation into numerous supernova afterglows containing pulsars further supported this conclusion. However, the afterglows of these cosmic events tend to fade much faster than the pulsating emissions from neutron stars, explaining why the majority of pulsars discovered today are not accompanied by a visible afterglow. To date, nearly 3,000 neutron stars have been cataloged within our galaxy, with over 2,700 of these being of the pulsar type. We are set to explore other varieties of neutron stars, which vary greatly in shape and characteristics. These small, yet incredibly dense stars are truly unique, standing out in their own distinct category. Since their discovery, scientists have observed that these fascinating celestial bodies tend to populate specific regions of space, adding another layer of intrigue to their already captivating nature. As we delve deeper into the study of neutron stars, we continue to uncover the profound and peculiar ways they influence the cosmic landscape around them. Neutron stars, though scattered across the Milky Way, much like other stars primarily along the galactic disk, hold a unique place in the celestial hierarchy. Unlike their more luminous counterparts, neutron stars are notoriously elusive, hinting that countless more remain hidden in the cosmic shadows. NASA estimates that our galaxy could be home to up to 1 billion neutron stars. In 2018, astronomers made a monumental discovery, the first isolated neutron star outside our Milky Way. Positioned within the small Magellanic Cloud, some 200,000 light-years from our Sun, this neutron star was identified amidst the remnants of a supernova that erupted nearly 2,000 years ago. This groundbreaking observation was made possible through the synergy of advanced technologies. By superimposing the X-ray images from NASA's Chandra Space Telescope with visible light data from the MUSE instrument on the Very Large Telescope in Chile, astronomers were able to capture and study the intricate details of this distant neutron star's remains. This fusion of data not only provides a clearer view into the nature of neutron stars, but also marks a significant step forward in our exploration of the universe. In the depths of space, within a gas cloud known as E102, an area familiar to astronomers, for nearly 35 years, a remarkable discovery unfolded. Scientists identified a second, much smaller ring of gas harboring a bright spot visible in X-ray imagery, a neutron star. While the presence of the neutron star wasn't entirely unexpected, its unique features captivated the scientific community. This neutron star is encircled by two asymmetric gaseous rings, each expanding at dramatically different speeds. The larger ring expands at a breathtaking speed of about 1,000 kilometers per second, approximately 620 miles per second, while the smaller ring, cradling the neutron star itself, moves at a more modest pace of about 90 kilometers per second, around 56 miles per second. Researchers are now busy comparing the energy spectrum of this neutron star with those of two other well-known stars within our galaxy. These comparisons involve stars located in the supernova remnants known as Cassiopeia A in its namesake constellation and Puppis A in the constellation Vela, both of which, like our neutron star in Eon 102, exist without companion stars. Intriguingly, this newly observed neutron star, detectable only through its X-ray emissions, does not emit radio waves, pulsar or otherwise, suggesting it possesses a relatively subdued magnetic field. This nuance adds yet another layer of mystery to the already enigmatic nature of neutron stars, continuing to challenge and expand our understanding of these celestial phenomena. Among all the neutron stars discovered in the Milky Way, only 10 exhibit characteristics as unique as this one. What captivates astronomers most is unraveling how this neutron star ended up so far from the center of the main ring and why it is moving, albeit slowly. Astrophysicists are exploring two possible scenarios to explain this mystery. One theory suggests a displacement or deformation of the vast shock wave triggered by a series of precise events that led to this asymmetry. Alternatively, it could be that the neutron star itself received a sudden thrust from a strong, asymmetric explosion, propelling it to its current position. This neutron star, the first to be discovered outside our galaxy, has thrust itself into the limelight, but has yet to divulge all the secrets of its tumultuous past. Let's delve deeper into the intriguing attributes of neutron stars. Despite their diminutive size, averaging just 20 kilometers or about 12 miles in diameter, their density is astonishingly high. This extraordinary density paints a picture of cosmic anomalies that defy the vast expanses of space, offering a glimpse into the extreme conditions that shape the universe. Neutron stars, often hailed as the relics of all extremes, exhibit a density nearly beyond comprehension, about 1,000 billion tons per liter. To put this into perspective, if a teaspoon of neutron star material were transported to Earth, it would weigh over 1 billion tons. These stars are not only remarkable for their incredible density, but also for their intense magnetic fields, typically around 100 billion teslas. For context, the tesla is a unit of measurement for magnetic fields, and to appreciate the magnitude of a neutron star's field, consider this: it is on average 100,000 billion times stronger than Earth's magnetic field. Another astonishing trait of neutron stars is their exceptionally smooth surfaces. This smoothness is puzzling, especially considering the intense gravitational forces you would expect to create significant surface irregularities. Yet studies indicate that any prominences on the surfaces of neutron stars are extraordinarily minimal. This combination of extreme density, powerful magnetic fields, and smooth surfaces makes neutron stars one of the universe's most fascinating and extreme phenomena. Imagine a world where the highest mountains are less than 1 millimeter tall. On neutron stars, these minuscule elevations are the equivalent of what would be less than 50 chem, or 20 inches, on Earth. With such intense gravitational forces at play, it's clear that life as we know it couldn't possibly exist on the surface of these extraordinary objects. Though they bear the name star, neutron stars are technically no longer active stars. True stars continue to perform stellar nucleosynthesis, the process of fusing elements in their cores, something neutron stars no longer have the capacity to do. As such, they are often considered the remnants or dying embers of stars. So, what exactly is a neutron star made of? Like all stars, neutron stars have a multi-layered structure with varying densities. Let's delve into the anatomy of a neutron star by starting with its outermost layer, the atmosphere. This layer is a mere thin gaseous envelope, so thin that its thickness is measured in centimeters. Sometimes referred to as a gaseous ocean, this envelope can reach temperatures of several million degrees. Despite its fiery heat, this atmospheric layer, under the crushing gravity 10 billion times greater than that of the Sun, surprisingly conceals a solid core, revealing the complex and intriguing nature of neutron stars. Beneath the surface of a neutron star lies an outer crust, an intricate structure similar in composition to the core of a white dwarf and primarily made up of iron. This layer hosts a network of highly ionized atomic nuclei and free electrons, forming a lattice that creates a crystalline structure. As the density within this layer increases, fusion reactions occur between atomic nuclei protons and free electrons, leading to the transmutation of these basic atomic nuclei into elements like nickel, zinc, or krypton, depending on the pressure and density they endure. When the density reaches overwhelming levels, the nuclei, now too neutron-rich, begin to release some of these neutrons. This transition marks the boundary to what is known as the inner crust. Here, the environment is dominated by extremely neutron-rich nuclei immersed in a sea of free electrons and neutron gas. This entire outer layer, split into two distinct zones, spans approximately 1 km or 0.6 miles in thickness. Below this region, the conditions become even more extreme. The density is so intense that atomic nuclei completely dissolve, merging into a bizarre state of matter, a superfluid neutron soup. This strange, dense mixture, interspersed with a smattering of electrons, forms a fluid layer that behaves in ways that defy traditional physics, illustrating the strange and fascinating inner workings of neutron stars. Diving deeper into the structure of a neutron star, we find ourselves in the outer core, an expansive zone about 10 kilometers or 6 miles across. This region is home to a superconducting proton gas that plays a crucial role in generating the star's intense magnetic field. At the very heart of the neutron star, we encounter the most enigmatic region, the possible solid core. While it remains a hypothesis due to the inaccessibility and non-observability of this inner part, we can make educated guesses about its characteristics by analyzing the star's mass and radius. For instance, a neutron star with a radius of approximately 10 kilometers and a mass about 1.4 times that of the Sun is thought to have a solid inner core around 1 kilometer in diameter. Here, neutrons might organize into a crystalline structure, presenting an astounding state of matter. Within this incredibly dense environment, one of the most intriguing questions is how the fundamental particles quarks, which make up neutrons and protons, rearrange themselves. Do they form new, previously unknown combinations? This mystery adds to the exotic nature of neutron stars, making them not only fascinating celestial objects, but also a frontier for theoretical physics, where the extreme conditions could lead to groundbreaking discoveries in particle behavior. Neutron stars are celestial speedsters, with rotation periods that can be mind-bogglingly fast. While some spin about once every 30 seconds, the fastest among them whirl around in just 1/100th of a second. This frenetic pace is a result of the conservation of angular momentum, the same spinning motion the star had before it collapsed. As the star shrinks, becoming smaller and denser, its spin speeds up due to the conservation of this angular momentum. Welcome to Blessovia Science TV, where we take you on an exhilarating journey through the cosmos and unravel the mysteries of science. We are excited to offer you the opportunity to become a valued member of our ever-growing community of cosmic enthusiasts and knowledge seekers. Exclusive access to cosmic content. As a member of Blisovia Science TV, you will gain exclusive access to a treasure trove of cosmic content, including documentaries, interviews with leading scientists, space missions updates, and awe-inspiring visualizations of the universe, live Q, and sessions with experts. Your membership will grant you the chance to participate in live Q and sessions with renowned scientists, astronomers, and space explorers. Get your burning questions answered by those who push the boundaries of human knowledge. Embark on a journey that spans the cosmos and join us in unraveling the secrets of the universe. Become a Blisovia Science TV member today, and together we will reach for the stars. Thanks for watching. Subscribe, like, and share. Don't forget to leave your comment.